Welcome back to the Knowledge Academy's YouTube channel. In this video, we'll explore 4 fundamental concepts: encapsulation, abstraction, inheritance, and polymorphism. Let's start with encapsulation. Encapsulation refers to the bundling of data and methods that operate on the data into a single unit, known as a class. This helps in hiding the internal state and requiring all interactions to be performed through well-defined interfaces. Now that we have a brief idea about what encapsulation is, let's see its importance. Encapsulation is crucial in object-oriented programming as it allows us to create modular and maintainable code. By encapsulating related data and functions within a class, we can ensure that the data is accessed and modified in a controlled manner. This makes the code easier to understand and debug. In dynamic environments where changes are frequent, whether driven by client demands or managerial directives, encapsulation enables developers to navigate swiftly to the precise areas needing modification. This targeted approach streamlines the process of implementing required changes, ensuring that adjustments can be made efficiently and with confidence. In Python, we achieve encapsulation by using classes. As you already know, a class is a blueprint for creating objects, and it defines the attributes and methods of those objects. Let's kick things off by exploring what happens when we neglect encapsulation. Let's dive into some codes to understand this properly. We start by defining a class named Book. This class represents a book object and contains attributes like title, author, and price. Now let's create an instance of the book class. We'll call it MyBooks and provide some sample information such as the title, Python Programming, the author John Doe, and a price of £50. To access the price of the book, we can simply print it out. Now, here comes the interesting part. We're going to directly change the price of the book instance. In a properly encapsulated class, this wouldn't be possible, but here, we're breaking that encapsulation. Let's see the consequence of this lack of encapsulation. We'll print out the modified price. As you can see, the price has been modified to £0, showcasing the lack of encapsulation. In Python, attributes of an object are not protected by default, allowing direct access and modification. In this scenario, anyone can alter the price of our book object easily. It's like having an open-door policy for data manipulation. As you saw, anyone might stumble upon our book and decide, hey, let's make this book free. Not exactly the outcome we're aiming for, right? Here comes the application of encapsulation. See, here's our revised book class. Notice the addition of 2 methods, getPrice and setPrice. These methods provide controlled access to the price attribute, ensuring that it's not directly accessible from outside the class. Now, when we create an instance of the book class, such as MyBook, the price attribute is still initialized as before, but it's now encapsulated, meaning it's not directly accessible from outside the class. To access the price of the book, we no longer directly access the price attribute. Instead, we use the getPrice method, which provides controlled access to the price attribute. If we attempt to directly modify the price attribute from outside the class, we'll encounter an error as it's now encapsulated and inaccessible. Oops, but it's not giving any error, nor is it changing the output. Why is this so? It's because of the concept of name mangling in Python. Name mangling is a process where Python alters the name of private variables, like __price, by adding a prefix _ class name. In this case, making it _book _price. So when we try to set price to 0 like here, we're actually not modifying the original protected attribute. Instead, we create a new unrelated attribute named _price. As a result, when we call the getPrice method, it still retrieves 50. Instead, we should use the setPrice method to update the price attribute. This ensures that any changes go through the proper channel, maintaining the integrity of our data. Now, let's confirm that the price has been updated correctly by using the getPrice method again. As you can see, by encapsulating the price attribute and providing getter and setter methods, we've enhanced the robustness of our book class, ensuring that data manipulation is done in a controlled manner. By embracing encapsulation, we fortified our book's defenses, safeguarding its integrity against unwanted tampering. So, whether you're just starting your coding journey or a seasoned veteran, remember, encapsulation is your ally in object-oriented programming. Moving on to the next concept, abstraction. Abstraction is the process of hiding the complex implementation, details, and showing only the essential features of the object. It allows us to focus on what an object does rather than how it achieves it. Abstraction helps in managing complexity by breaking down a system into smaller, more manageable parts. It allows us to design and implement systems in a modular and hierarchical manner, making it easier to understand, maintain, and scale. Abstraction in Python involves defining abstract classes and methods that serve as blueprints for child classes, allowing developers to outline essential functionalities without detailing all the implementation aspects up front. Let's see how abstraction enhances our code. We'll begin by defining a base class named Shape. This class serves as a foundation for various shapes and provides placeholders for calculating their areas and perimeters. Next up, let's create specific shape classes for circles and squares. These classes will inherit from the shape class, which means they'll have access to all the methods defined in the shape class. This concept of inheritance will be explored more in depth later in this video, but for now, just understand that all methods defined inside the shape class will also be available in its child classes. With our shape classes defined, we can now create instances of circles and squares and calculate their areas and perimeters. By exploring these shape classes without abstraction, we gain insight into the implementation details of each shape's calculations. While this approach can be informative, abstraction provides a more high-level and simplified interface. In this example, we have a shape class with specific implementations for each shape, such as circle and square. However, there's no enforced blueprint that mandates the inclusion of the area and perimeter methods in the child classes. Let's see how can we solve this issue using abstraction. First, we'll import the necessary module for working with abstract base classes. We then define an abstract base class named Shape using Python's built-in abstract base classes module. This class serves as a blueprint for other shape classes and defines two essential methods, area and perimeter. Now, let's create specific shape classes that inherit from our abstract shape class. We'll start with the circle class. The circle class represents a circle shape. It implements methods to calculate the area and perimeter of a circle using the provided radius. Now, let's move on to the squares class. The square class, like the circle class, inherits from the shape class. It calculates the area and perimeter of a square based on the length of its side. With our shape classes defined, we can now create instances of circles and squares, each with its specific properties, and easily calculate their areas and perimeters. But this is failing here. Why would that be? Python will not allow us to create an instance of square because square does not implement all of the abstract methods from its parent class. Specifically, square is missing an implementation for the perimeter method. Abstraction allows us to create a common interface for different shape classes, promoting code reusability and making our code base more maintainable and organized. In this improved version, we've introduced an abstract shape class with abstract methods for calculating area and perimeter. By embracing abstraction, we can create more adaptable and maintainable code, paving the way for future enhancements and improvements. Now, let's delve into inheritance. Inheritance is a fundamental concept in object-oriented programming that allows a new class to inherit properties and behaviors from an existing class. This promotes code reuse and helps in building hierarchical relationships between classes. Inheritance facilitates code reuse by enabling us to define common attributes and methods in a base class, which can then be inherited by subclasses. This reduces code duplication and promotes a more modular and organized codebase. In Python, inheritance is achieved by specifying the base class in parentheses after the subclass name. Let's see how inheritance works in practice. We define a base class vehicle with an initializer method in it that takes parameters brand and model, assigning them to instance variables. Next, we define a method displayInfo, which will display the brand and model of the vehicle. Here, we define a subclass car which inherits from vehicle. It has its own initializer method that calls the initializer method of the parent class using vehicle.init. We create an instance of car with brand Toyota, model Camrys, and year 2022. When we call display_info method, it prints the brand, model, and year of the car. Let's delve into the importance of the super function in Python and how it simplifies inheritance. We start with a base class vehicle that represents a generic vehicle. It has an initializer method in it that takes parameters brand and model and assigns them to instance variables. Next, we define a subclass car which inherits from vehicle. Here's where the super function shines. It allows us to call the initializer method of the parent class, ensuring that the initialization logic from the base class is also executed, maintaining consistency and avoiding code duplication. When we call display_info, it prints the brand, model, and year of the car, all thanks to the super keyword ensuring proper initialization from the parent class. By leveraging inheritance, we can create a hierarchy of classes that reflects real-world relationships, making our code more intuitive and easier to maintain. Lastly, let's explore polymorphism. Polymorphism allows objects of different classes to be treated as objects of a common superclass. This enables flexibility and extensibility in our code, as different objects can respond to the same message in unique ways. In Python, polymorphism is often achieved through method overriding and duck typing, where objects are evaluated based on their behavior rather than their type. Let's see polymorphism in action. Next, we have a method speak within the animal class. However, it's left blank for now, as each specific animal subclass will override it with its unique sound. Here, we define a subclass dog that inherits from animal. It has its own initializer method in it, which takes parameters name and breed and assigns them accordingly. The speak method of the dog class is overridden to return woof, representing the sound dogs make. Similarly, we define another subclass cat, also inheriting from animal. It has its own initializer method in it, taking parameters name and color. The speak method of the cat class is overridden to return a meow, representing the sound cats make. Now, we have make_sound method that accepts any object of type animal and calls it speak method. This is where polymorphism comes into play. We create instances of dog and cat classes, and when we pass them to the make_sound method, they each produce their unique sound, demonstrating polymorphism in action. In this example, we have a method speak that accepts an animal object as input. Despite not knowing the specific type of the animal, the method can still call the sound method, and each animal object responds with its unique sound. This demonstrates how polymorphism allows us to write code that can work with objects of different types, promoting code reuse and flexibility. That wraps up our discussion for today's video on object-oriented programming using Python. We've explored the fundamental concepts of object-oriented programming, delving into encapsulation, abstraction, polymorphism, and inheritance. In the next part of our series, we'll embark on an exciting beginner-level project that will vividly demonstrate the concepts of object-oriented programming in action. If you enjoyed this video, hit the like button and subscribe to our channel for more exciting and informative content. Don't forget to turn on notifications so you never miss an update.